Now we're going to be getting to probably one of the back to the sort of practical part of the course. I mean, we've gone through quite a few sort of theoretical relationships, talked about sensitivities, and immediately after this, we're going to go and get into the first exercise. And this really has to do with what we sort of call trending and sort of the first step in the analysis. So
I hope that you're firmly believers now in the validity of the Gaussian equation. So we got one piece tied down here with that logic slide, right? Now we're going to talk about the next piece, which is what do we need and where are we going to get it from to enter that Gaussian calculation so we can do this leg that goes up in a calculated reflective. That's it. So now I'm going to present some stuff here, and Mike's going to have a little bit different take on certain of the language, but I'll present the way I think and try to accommodate what, a broader definition, which Michael's on, but I welcome your intrusion, Mike. So trend curve. What's a trend curve? Why are they constructed, and how should they be constructed? I think you already know why they're constructed, because we've been talking about Gaussian all day. So we did this. I just now said we're going to look at that. What's a trend curve? Fluid substitution calculations, we know this. We need the dP and we need that porosity. And we need corresponding values. That's important. Estimation of the properties of pore fluids requires a knowledge of such parameters. We did this today too. We looked at the fluids and we found out, damn, I need to know the water salinity everywhere if I'm going to make good estimates of the beta that I get out of my brine saturated velocities. In order to estimate the proper amplitudes for oil, I'm going to need to know things like the oil gravity as well as temperature and pressure. You need to estimate these things for a potential reservoir at any depth of time on your seismic section at any place in your respective area. You're looking at the seismic and say, hey, there's some amplitude. I think it fits structure. I want to do this analysis. It could be anywhere. It could be at any time. It could be in any place. The trend curve is going to consist of an empirical relation derived from the data. Now, pay attention to the words, which allows one to predict these properties for every possibly occurring rock type as functions of depth at any prospective location. I normally, and you'll see it later, think of trend curves primarily as functions of, as properties written down as functions of depth, but they don't have to be. They can be functions of other parameters which you think you can estimate at any depth, okay? They can be more general relations, so long as you think you can predict them at any time. Most commonly, wireline log velocity and density data for various rock types are picked from the logs obtained in previously drilled wells and plotted as functions of depth. Curves representing the systematic variation of these properties are then derived from these data. Okay, obviously there's going to be a lot of issues here, so let's talk about some. This is an example of a log. This is a very old log. I got it back in the 70s someplace. This is from the Rocky Mountains. This is depth in feet. This is a SP log with a big old sand. And the resistivity, I think normal resistivity, gosh, I can't even read it. This is the resistivity right here. You see the upper portion turned out had gas. The lower portion did not. Had water. This baby's about 100 feet thick, I think, not quite. This is the caliper that had a little bit of a problem in here. This is a transit time log in the 70s. This is the gas-water contact right here. You can see a much, I don't know if you can see it, I can't even read it. This is 140, this is 240. 40, 140, okay? So, this is high transit time, this is low transit time, this is lower velocity than this. That's what we expect, right? Gaussian in a porous rock is going to give you. So right away I asked the guy, well, what's the velocity of that rock? And I'm showing this picture here because I said, well, how would I pick this long, how would I pick my end member for a trend curve? Well, I want to assemble rock properties for the sands and the shales or other sealing rocks that are in my section. All the rock types that are in my section. That's very important, as we'll see. Well, I'd be picking this for my brine saturated sand. That's where I'm going to get my case of M's from, right? That's my transit time for my brine saturated sand. Got the other sands here? There's a sand down here. That might be another one I could pick. I don't have the rest of it, but you know, if it's good enough, it's a good clean sand, which I think it's good response. I'm going to show you the rest of this since it's on here. It's sort of problematic, but here's a pig. Here's a pig. This is a pig. I put a brown pig here for a shale of some kind. That's up here. It's got high resistance. This is a cycloskip. That's what we used to have. So I got a porosity from the gentleman in division at the time, and he said the porosity is 30%, and he thinks the water saturation is 44%. That was an analysis of the conductivity law. And so I did the velocity calculation using this with this porosity, Gaussian substitution for gas, and I got that transit time. Well, that's not this, that's for sure. So then I started to do some sensitivity, and I said, suppose this isn't the right number. I don't know which one I did first. I said, first, suppose this is right, and that's not right. How much would it have to be changed in order for this to go over to here? Suppose this is right, and this is wrong. How much would I have to change this in order to make this go over here? That's the kind of sensitivity analysis I did at the time. That shows you these two results. This one, you hold this one constant. You have to change the porosity more than I think is reasonable. I think they had some sidewall cores. But you could get a lot closer. I mean, 1 or 2 porosity percent would certainly be reasonable variability. And here you would have to change the saturation a lot. But that might not be too hard to do because you're not seeing that far into the formation of the resistor. You're going to flush it. So anyhow,
So Mike, so
the point, none of that is very important. The point,
yeah, but why is it slower? Or is it faster? So is that faster or slower?
no, this is slow. This direction is slow.
Okay.
Okay.
So why is it getting slower with less porosity?
Slower than we estimate.
Yeah, with less porosity. As you decrease the porosity, it's getting slower. Porosity's gone from 30% to 27%.
Yes, if you decrease the porosity, but you hold the velocity the same, you're going to get a smaller beta. If you decrease the porosity, but you hold the brine saturated velocity the same, the rock has to be weaker. The matrix has to be weaker at that lower porosity. You have more solid material. That's what you're saying. So beta has to be weaker to give you that. Has to be smaller to give you that. So you would get a bigger Gaussian effect. That's what. Do think about it. We'll talk. I've heard that question 40 times if I've heard it once. Not related to this, but that is over my career. A fellow called me up one time and said, your program doesn't work. I've been programmed to, he says, your program's got a bug in it. So we talked on the phone. He was in the Los Angeles office. I was interested. We talked for a while, and I asked him some questions. Eventually, when we got all done, I'd explained it to him, and he had understood it. I said, so you see the bug was in your head. It wasn't in my program. But it's not obvious. And it's a good question. Okay, trend curve example. So we picked some points. I mean, this is just a cartoon. All what you see now is cartoon. Imagine we had some data like this. Well, we might draw some curve through here. Could be a quadratic or something. Characterize the data in some way. There's going to be variance around it. Why is that so? It's not errors in the log measurement that primarily cause this kind of variability. It is variability in geology. If you look at the rock, you'll find out that the rocks aren't deposited exactly, they're not all the same exactly. And you see what sometimes they have variations. So trend curves, some of the essential features of this kind of trend curve business are, there's going to be variance or scatter of the data. You want the relation to be systematic. If it's not systematic, you really can't predict very well from it. I'll say what I mean by systematic. All rock types must be represented. Boy, if there's one here you want to really focus on, that you should be thinking of when you are picking logs for trend curves, you be thinking of that guy. Data must be representative of a prospective area. That's an issue of, you have a big area to prospect over. You have a limited number of penetrations. There can be spatial variation in the parameters, in the rock character. We just saw that case. What is that Saba example that we had there, Mike? That the last slides there.
It was in Brunei.
Brunei, okay. That Brunei example, that there was stratigraphic variation. You remember that brighter stuff off here up in the right-hand corner? And we said, well, that's not structurally conformable, and we don't think that that's hydrocarbons. That's the conclusion. That's stratigraphic variation. It's a spatial dependence of the rock properties, and that's quite common, stratigraphy varies. Velocity and density may be separately estimated, must be separately estimated. This one, I'll back off on that a little bit. If you're hard against it, you know, you can use velocity density relations in some cases to get the density if you know the velocities, but it's much better to have pairs if you have simultaneous pairs, a density and a velocity for the same interval in the same way. Okay, systematic variation, what's that? That's a systematic variation with depth. This one has deviations, which are systematic from a simple curve. So there's more than one relation here. This is a systematic variability. This is a different trend. This is a different trend. This looks like thrust sheets or something. You know, that's when you see data that are grouped like that, you can't draw a line like this and predict it, because these separations may occur at different depths if you're doing things against depth. You know, somewhere else in the area you're prospecting.
But, sorry, to that, and coming back to the last point, all rocks must be representative.
Yes.
You're going to speak about when it's time to cluster things and when it's time to
Yes,
break
I will talk a little bit about that, and also about all rocks. So let's go right through.
What was the question again?
He wants to know, when should you conglomerate data? When should you join it together and use trends that are characteristic of the whole, as opposed to when should you separate them out and say, hey, I think I have spatial variation here, right?
Yeah, or facies variation.
Or what? Or facies variation, absolutely. Yeah, and we talk a little bit about that.
I think though part of it really is sort of shown here, that whenever you go and if you group data together, that really is, you know, as you can see, it's sort of a random variation around a line. That's probably good data to group together. When you go and start seeing something like this, I would always, where you literally see where I could fit, this seems to be one thing, this seems to be something else. This always speaks to me that there's some way to subdivide this, or there's some thrust sheet, or there's something happening, and that we need to go and start splitting this out or understanding more carefully what's causing the variation on the right-hand side. So.
But let's keep talking, and we'll come back to that. It's a good question. Okay, all rock types must be represented. This is very important. In clastic basins, very typically, this can also happen in carpets, but in clastic basins, very typically, you focus in on a sand shale sequence, and you'll say, hey, I got sands, maybe I got siltstones, and I got shales. I may be able to recognize the type responses of all three, sort of generate transfer. But you may also have other rock types that don't occur frequently. So you may have a deltaic sequence that's 8,000 feet thick, and then somewhere down here, or, you know, a whole sequence of cycles altogether, packaged that's 8,000 feet thick. And then you may have even an unconformity or something, there may be a volcanic or something down there, and maybe there's only one volcanic layer or two, but if you got volcanics in that section, and those volcanics don't occur at the same depth all the time, you better have the volcanics in your mind. That's just what I call a sport rock. If there's salt beds, at one point you had an evaporite deposition, you'd better be thinking about salt as possibility of that section, and where does it lie in this trend curve business. So when you see unusual rocks on your logs, say, well, that doesn't fit, that's not my shale, that's not my sand. Think about that rock, which you see a consistent log response in, that's longer than the response of the tool. It's a 50-foot thick unit, it's got a funny looking log response that you're not sure you've seen, and mark that baby and say, I'm gonna come back to that and wonder what it is. It may be a combination, it may be a laminated rock, it may be a simple layered rock, a mixed rock. We're going to treat that later. But it may also be a sport, what I call a sport rock. It may be something you're not thinking about and you need to think about because it could happen elsewhere and so on.
And also when Dave talks about a sport rock, that what's considered our business rocks are sands and shales, especially sands with hydrocarbons in it. And the rest are just things that you worry about for sport. But one person's sport may be another's business, as you find
Here we
out
come.
in the slides.
So here's my little cartoon. I have a bunch of points here. I got a nice bunch of shale picks, and I got a nice bunch of blind sand picks, and hey, they look like they trend pretty well. I got a little variance, but I can live with it. And then I say, great, I'm ready to do my Gossman deal, and I can transform this baby if I have, this is velocity, but I have a density one too. I can take this curve point by point with its porosities, velocities, and generate this curve over here with Gossman, right? So my gas sand's gonna look like this. Yeah, so there it is. I see something right here, and it has an amplitude that's right about there, right? I say, hot dog, that could be gas. That may even look like it fits my structure somehow. And then I drill it, and I find out there's coal over there. And coal looks like gas. And I didn't think about coal because it doesn't occur frequently in the basin. So, but if it occurs, you better identify that that's what it is, and say, oh, there's coal in the basin, or there's salt in the basin. I better be thinking about that. Could occur.
Is there an explanation for coal to be like gas?
Yes. What do you mean? Is there an explanation for
Well,
it?
on that one, I mean, they look like
It's
gas
just
in terms of
it's
velocity.
the way God made it. That's the best I can do. That is, the elastic moduli of minerals are the elastic moduli of minerals. I can't change them. Coal is light. It's a very light material, so it has a much lower density than normal rock. Salt, sodium chloride. You know, look, minerals. Most of the clastic minerals, feldspars, clay, sandstone, have densities like 2.65 to 2.7. Limestone's 2.72, by the way. And salt has a density of 2.15, so grams per cubic centimeter. So salt, sodium chloride, is less dense rock. It has a pretty good bulk modulus. It's tight, doesn't have any porosity. Coal has typically got pores in it. It's got it's weak. It has a low bulk modulus too. So if you look at the table in the what is it, the appendix there, in the supplements, you'll see some numbers for coal, and you'll realize they're soft and they're softer, like gas sands, even in soft rock. But as to you know the particular structure of coal and why that is, I can't help you. That's just the way it is. Here's a question that Derry was asking: what can I do? What can I not do? Right? Suppose I have 2 wells. Naturally, your inclination is, damn, I've only got 6 wells in this whole area. Or you're lucky if you got 6 wells, right? But I only have 6 wells, and there's a big 300 square miles or something, and so I gotta know, I really hope that they all have similar properties, so I don't have to go fooling around with geographic variation properties. Well, there's two wells, so I get a velocity versus depth in well 1 and get a velocity and depth versus well 2. One procedure I think you should always follow is to fit your wells separately and then compare well to well for whatever variable you're trending against. If you're trending against depth and against depth, if you're trending against differential pressure, just overlay that well on this well for whatever property you are trying to determine, density or porosity or velocity, and make sure that they are corresponding. In this case, they wouldn't be. You'd have to say, I think there's variability in whatever I picked for this rock type. And well 2 has different properties. Perhaps it has a higher, a lower porosity and a higher density.
Well, ask, I mean, Tim, what would cause, if you were looking at a velocity versus depth profile, you saw a shift like that, what would be the first thing that you might think? What would be the difference between those two wells?
Different burial histories, different.
You think the sands are connected and on the same, to the same aquifer?
Different facies.
Is that?
Different facies.
So they could just
Certainly
really be
possible. We're going to come to that in a minute.
Yeah, well, I mean, another thing too is that they could just not be on the same, you know, aquifer, and there's different pressures at the different depths too, is another common thing that can happen, if that was velocity versus depth. Things that you were talking about probably be more representative if you're looking at like a VP versus density. Here, I mean, the first thing I'd be thinking of would, yeah, especially if I saw that, a very simple thing is there's just different reservoir pressures. So,
Uniformity, maybe one goes a little bit to that.
Yeah,
that's also a
and
possibility.
now, of course, you'd look at your seismic, what have you, I think you should always do this in terms of looking at the seismic and trying to get a feel for what the basin looks like before what the geology would look like before you just apply your data. Okay, here's some other issues. Should one use absolute or relative definitions of quote rock types, unquote? And I just sort of, I should have put this in parentheses, a trade-off between sampling density and accuracy. Should one characterize the whole log or just selected intervals? Characterization of all naturally occurring rock types, including sport rocks, we've talked about that, I just repeated myself here. What corrections should be made to the raw data, if any? That's a good question. How should the data be grouped? That's what Terry's asking. Trade-off between variance and geographic generality. What steps may be taken to assure quality control? I'm going to deal with some of these, at least, in the next few cartoons, and that's all they're going to be is cartoons. What do I mean by absolute versus relative rock type definitions? You know, what you'd really like to have, forget this, I'm standing in front of it now, look at this. What you'd really like to have is, oh, I've got some cores over here, and I have a log, or two, in this well, density, velocity log, and by golly, I know what's a clean quartzitic sand, because I got the core, and at this depth, this depth, this depth, and this depth, I have that clean quartzitic sand. There's less than 5% feldspar or clay or whatever the hell it is. There's no pollutants, no nothing. I know what that rock is mineralogically. I know what it means. I'm going to trend that for my clean end member cores. Okay. Maybe I have two other picks, and I look at the cores and I say, these guys are carbonate cemented. Mark was talking about cemented rocks earlier. They have a different trend. Often I don't have that. In fact, almost all the time I don't have that. Nobody got those cores. Very rarely do you have that kind of information. More commonly what you have is some logs. And what you do is to say, look, I know I'm in a clastic section. The dominant rocks here are shales, siltstones, and sands. I'm going to look at the sands, and I can identify those with SP and gamma ray, and particularly the soft rock basins where we're dealing primarily for looking for DHIs. And I'm going to pick the most extreme responses. That is, the ones with the biggest deflections in gamma rays. And those I'm going to call
Gonna have to stop in a second.
end number sands. That's what I call a relative relative rock type definition.
It's always here.
Relative
It's
rock.
inside
Best
and
quality
it's
sand
inside.
observed in the section, whatever
Then you
best
can't see the
quality.
soil.
It's a wireline log-based criteria.
Okay, I've got to stop it.
What's the problem? IWB. So this works best if you have a depositional machine which drops all the rock types that you're going to see in that machine laid down, that geological machine laid down, within short intervals relative to the length of your log. Then you're going to pick the best rocks that machine drops. Ian, you got a question? Fine. So that'll work well that way. When will it not work well? It'll work not very well if either what I just said happens, or doesn't happen. That is, you have 4,000 feet of log, and you have a single delta depositional cycle that was for 3,000 or 4,000 feet long. That's when it's not going to work very well, because you'll only have one, maybe two sands. It's not going to work very well if you happen to have drilled a well where you only have one sand and a heck of a bunch of shale, but elsewhere, that same depositional machine has dropped a lot of sand. You're going to pick some poor quality sands, some silty rocks, and call them sands up here, because you're not going to necessarily recognize that this isn't as good a response, a clean rock response, as this guy down here, 4,000 feet deep. Now, this thing can be fought with peril, and you should be thinking about it, but you are going to be forced to do this. So whenever you have core information available, mineralogy, sidewalls, look at it. Okay, when you've done some trending, look at that mineralogy of that core and say, oh, I can fish those up. It won't take an hour and a half here to go down to files and get it. I'm going to look at that stuff. Oh yeah, this one, and this one are all clean rocks. That guy's a different thing. It's a different animal. I'm just doing that. Oh, okay.
Well, that's one thing though, and with respect to the mining application, since there is much more whole core, it's not as big of
Yeah,
a
it's a
problem
different
as it
story.
is for petroleum.
It's a different
so-
story for mine. Yeah, I agree with you. I'm talking petroleum exploration. You'll have core, you should look at it. We should look at it. Okay, relative rock type definition will generally increase the scatter and the variance. I think you can understand that. Why? It relies on this idea we talked about. And it's widely used because sufficient petrographic data for a robust sampling using absolute rock class definitions is frequently unavailable. You may have, if you're lucky, 3 or 4 wells to work from in which you have logs. And if you have core in a couple of intervals of one of them, you'll be lucky. So you're just not going to have this information for absolute. But check that information if you have any of it. Okay, trend curve corrections. I have my own pet peeves. Different people have different views on this issue. I will talk to you about what I think. Look, you're going to have to live with variance. That's part of the game we're in. Mike talks about Bayesian and uncertainty in the measurements. If you tell me 2 measurements are different and you don't tell me anything about the uncertainties in the measurement, there's no way for you to tell me that the 2 measurements are different. You have to tell me what the uncertainties are. So you have a vested interest in trying to reduce the uncertainties of your measurements and of your measurements of seismic data and your measurements of rock properties data from which you're going to make predictions on what the seismic amplitudes ought to be. Because that's going to sharpen your discrimination. Reducing that variance is going to sharpen that discrimination capability. So you don't want to allow your data to have any more variance than you must admit. That it's caused by geology and things of that nature. So first, if you have different passes, not modern logs, you have all these things running the same pass, but in older wells, you may have a density log on one pass and a velocity log on another pass. Make sure those logs are aligned before you start picking common intervals, because you'll mix in shales with sands and get the wrong numbers. Of course, I say measurement errors, I should change that. I should say, you should try to make corrections for hole size and mud weight variations between wells. You want to compare apples with apples. These things often affect significantly the measurements, and the corrections for them are known, and Schlumberger or whatever have tables for this. Delete data which does not pass quality control tests. We'll talk about that in a minute. Never ever make, this is a pet peeve of mine, you're going to make catalogs, the software that Mike will show you, that allows you to make, you call it databases for the logs you pick, and that's very valuable to subsequent investigators and people in other basins and everything who are looking at analogs. For gosh sakes, don't put a subjectively edited data into a database, because the next guy comes along, wants to use that data, and you've made a subjective edit he doesn't know anything about. It's not really the data at all. If you think that the data are an error, don't include them in the database as your first pass in constructing a term. And just don't pick in intervals where clear logging tool malfunctions have occurred. You'd say to yourself, that's ridiculous. Who'd do such a thing? If you only have one sand and you only have one well, you're going to be tempted sorely. And if you got a crappy washout and a lousy stinking caliper, watch out. That's all I'm going to tell you.
Yeah, let me sort of the second to last one too. I mean, Dave did talk about it. I'll give another little particular take on it. It's also probably one of my pet peeves when you're doing this, is that if sort of the fewer the better, okay? Sort of part of the BHP style is what Dave is going to be showing, has shown and will show, is that we go in and don't go and pick every particular sample. We try to go and pick sort of generic intervals. And also because of that, we have a lot fewer data points. It also means you should go and really go and respect each of those data points. And if you're going to throw out a point, have a good reason. To throw out a point just because it sticks out, okay, is not a good reason. That's a subjective edit. And you really need to go back, was there a data entry problem? Is this a sport rock? What's causing this? Was there a bad measurement? Was there a hole washout? And on the basis of that, eliminate it, okay? I think, though, that you'll go and see, especially in packages where you pick every foot, that you get tempted to just sort of cast out numbers that just sort of stick out. Here, you really have to ask hard questions about every point, and especially every point that you decide to exclude.
Yeah, and that's very, very good, very good comment. And I want to add one more thing to it. If you're looking at a log, and you will do this because you guys are going to be interested in this direct hydrocarbon interpretation business. If you're going to do this, and you are looking at data and saying, that point sticks out, I don't know why, don't try to solve the problem as an ersatz or what do you call it? We call it shade, in Texas we call it shade tree petrophysicist. You go out and sit under the shade tree and look at the log and figure it out. Go to your petrophysicist, he's an expert, you understand, in interpreting logs, and ask him, why is this response different than all these others that I saw? Is there a reason? Or if you're sufficiently familiar with the logs, you might be able to figure it out yourself, but don't be afraid to ask that guy to help you understand it. Okay, quality control. I said I was going to say something about quality control. Well, I think I put this in here a long time ago. I think this is almost automatically done now, but it never hurts to look. You should always check your log calibrations if you have 3 wells and if the tool wasn't reading density right. The calibration section, that's a big mistake in one of them. You're going to get those different trend curves, and you're going to think that's meaningful on its own. Comparison of synthetics with deconvolved size of data is very important. We're going to talk about synthetics tomorrow, but you really need to do that. If you make a synthetic seismogram from a well log, which you commonly will do, we're talking about this over here. Different seismic trace, but we can also make that seismic trace from these well logs and then just band limit that son of a gun to the same band limits as the seismic data and say, okay, now, how do they compare? Now, where I have a coherent reflection event on the seismic record, I should see an event from the log. That's a primary reflection. If I don't have an event from the log there, if I have just a little bump that looks like noise, I have a real problem. Either there's been bad amplitude preservation in the seismic data processing, or the whole isn't representative of that section, or the log had a malfunction in that particular zone. Logs read correctly in good holes 95% of the time, but ask a petrophysical engineer. They don't read correctly at every foot, I can tell you that. So
There's also another very good, I think,
So
example.
this is very important, that's all.
There's also a very good example here of something that was picked up, and I think Guy Duncan has noticed a couple times of where that there could well be low saturation gas in the formation that wasn't read by the well log. And when you look at the particular synthetic, there's a much larger reflection than would be indicated if you just simply looked at the well log.
Yeah, on the seismic data, there's a larger reflection than you
Yeah.
see on the synthetic.
Yeah, and then you would see on the synthetic, I'm sorry. And, that's also leads you, to sort of have a particular alarm bell, and also can lead to some better understanding, so.
True. This is another one, in very soft rocks. It's a real good idea. It's a very, should I say, it's a sort of a crude check, but it's an important check. It's a very good idea, particularly if you're using short interval borehole compensated science, not long interval compensated science, or better yet, we call it Tensor-Mizaki type tools, monopole type things, which are done at much lower frequency, deeper penetration in the formation of that's kind of lossy log you can get. Very good idea to look at the comparison of your integrated velocity logs with VSP, vertical seismic profile, or check shot survey times for an interval. You know the depth and the time on the VSP. You know the depth on the log between those two depths. You can integrate the transit time log and compare that integrated time to the time difference on the VSP, the seismic survey. Those two times should compare closely. If they don't, there's a problem. And the VSP is most often the proper one, because that's what you're trying to measure, the velocities of the seismic seed. Now, it can be something simple, like there is variation at some particular depths in that interval, local variation, where the log is seeing a rock that the seismic, which is sampling a much larger area, is seeing a different, but the rock's not homogeneous. The facies are varying at that particular level, as Ray was suggesting. So it can be something like that, but you may be able to recognize that by looking at the seismic. It can also be that the logs aren't reading properly, and in soft shales, this is not uncommon, particularly shale. Differentiate pit values from different wells before grouping, and check them for consistency. We talked about that one. Check correlations, that's quality control. Check correlations between the properties on different logs. That's good. Enough said. Remember, velocities and densities are affected by all these three things. Don't mix pits with different pore fluids, that's my advice. If you certainly will be tempted, and if I were running up against a situation where I had 2 sands and 2 wells, and that's all I had, one was at 4,000 feet and the other's at 9,000 feet, and that I say, well, I think that I should have some hydrocarbons. I got to get some sense of what to expect. There are 2 ways to go about doing that. One is from the imaging velocities, and I will talk about that a little later, and some other things you can stick in there. And another way is to say, I'm going to use those 2 sands, but one of them's got gas in it, and I'm going to use Gosselin to do the fluid substitution the other way. I'm going to take my water saturation with the gas as my input, calculate my matrix moduli from those, stick it in the brine that I think is characteristic of the basin, and calculate what the brine saturated velocity ought to be at that 4,000 foot depth for that well. I would do that if I only had those 2 points, but be careful doing that. So here's quality control for relative peaks. I have two L's. I want to compare, are these trends the same in each row? You can overlay them. This is tough. It's hard to think of cases that will do this, but they exist. We just talked about one in the, what was it, the Cascade Chinook kind of thing. But are the relations between the rock properties the same? Well, if they're not, it doesn't have to be density, velocity. It could be something like resistivity and velocity that you compare and you say, hey, they're quite different. That would form some reason for doing some separation, geographic separation. All right. Last thing is, I want to show some results of the Gaussian substitution business using some trend curves that were picked in this fashion. Sands, clean sands. This is the Zangola trend again. And what we're going to try to do, I'm going to try to give you some feeling. Everything's going to be plotted against water saturation at the bottom. And we're going to do a series of, a series of graphs. The last thing I need to do is lose my voice. Huh? Here we're going to look at the change in the density, and then we'll look at the change in the velocity, and then we'll look at the change in the beams. So first of all, there's no change from brine to brine, and it's just linear. And these are the depths. Over here I've got pure hydrocarbon. This is for brine to gas. What's the change? Okay, 0.2 to 0.25, something like that. What's the density? Up here for a reasonable porosity, 2. For a high porosity rock, 30-40% porosity rock. So only a 10% change. That's what we were talking about when I was talking about that first factor in the gospel. Here's the delta V, delta V2, change in velocity. This is in kilofeet per second. And you've seen this before. Remember what we had in the laboratory data where they came straight down? And we didn't like that so much, or it was hard to understand that. Well, this is the reality. After we have some rocks, even at 2,000 feet, there already is substantial density and modulus in the gas. And so you get some rounding of these curves. Okay, the next one is delta rho Vp. This is acoustic impedance. That's from it. Now we're going to put them all on the same basis. We'll talk about delta log rho. Delta log rho V. The change in the log rho V is, we make the logarithm functions real nice because it goes from a multiplicative relation to an additive relation. So we can say that's delta log rho plus delta log V. So let's look at how that goes. How much, in other words, does density contribute to the change in reflectivity compared to how much does velocity contribute to that change? And how does that change at depth, with depth, in a typical soft rock plastic basin? That's what we're looking at. So here's density. You're going to see the same scale over here on this side. Here's delta log rho with delta log Vp. So I got a huge effect at 2,000 feet. Not much effect at 10,000 feet. Let's go back to the last one now. Here's 2, here's 10. Here's commercial reservoir over here, residual water saturation or something. Let's just switch back and forth. Oops, that's gone too far. I went the wrong way. Where is it again? So over here, density is every bit as much of an effect as velocity. In fact, bigger. It's a little bit bigger. But certainly not shallow. If you compare those two in your book, you'll get a good feeling for that. So here's the combination of the two of them, delta log rho V. And here's what we said before. It's the third time we're making this point. Here's commercial. Here's non-commercial. You can see a lot of difference. From here to here is pretty much the same as from here to there, right? Not much difference. 4. Not much difference in 6. Some difference at 8. Almost no difference either. So you're not going to be able to tell the difference between a spun-traveling gas and commercial accumulation based upon amplitude alone. There are other clues. Okay, a few more slides, and then we'll get into the exercise. There are a few other relations that you can use when you are missing data and you're trying to generate it or need it. This figure is from a classic paper by Gardner, and Gregory in 1974. And it shows, you know, if you can't correlate things well on a linear scale, take the logarithms. Compress those scales. So what they're looking at is a whole bunch of measurements of density versus velocity for different kind of rocks. And they put together this thing. Here's sodium chloride over here. Here's anhydrite, it's a little off the line. But dolomites, limestones, sandstones, and shales tend to group in this space, and here's a dashed line that goes through them, and the equation of that line is here, and just for good measure, I'm going to stick it up here. It's coarse, but this is often termed the Gardner-Gregory relation for sedimentary rocks. Density is 0.23 times velocity to the 1/4, VP to the 1/4, where these are given in certain units, right? Density is in grams per cubic centimeter, velocity is in feet per second. Okay, or it's simple, if you want them in metric unit velocities, you can just change this constant appropriately, right? The key thing to understand here is that because of the way this relation works, if you know the velocity, you can make a pretty good estimate of the density, though not the density difference. You can't use this relation if you look at the back one, at the back slide. You can see where the sands are on this side. The sands are on this side of this dashed curve. Shales are on this side. So the density difference, you won't get that good an estimate. But better enough. If you have the velocity, the transit time law, you believe it, you can make a horseback estimate of the density, and you'll get some reasonable number. It won't be way off. Don't try to go the other way, because a small error here produces a huge error over here, and it's that bulk modulus that you want, and that goes as a velocity squared. So you're killing yourself. You're just introducing fraud error. Don't try to estimate velocities from densities using John Castagna and Mike Batzel, Mr. Eastwood, in 1985, published this relation here. It's a simple linear relation between VP and VS for what they call mud rocks over a wide range. Mud rocks are siltstone, shales, that kind of material. And you see some of the measurements, including things that are quite indurated rocks all the way to fairly soft rocks. You can estimate, I think, with this, you commonly may have a VP, you can make an estimate of the VS for such rocks. That's important sometimes in the data. Here's a measurement of some laboratory data in transit times of shear versus transit times of compressional waves on the abscissa for different rock types made by Pickett way back in the 60s, I think, 63. And these are lines of constant VP to VS ratio. I said something before about sigma sub m's for limestones being almost at any porosity 0.3, and dolomites a little less. And here's where you're going to see it, where the limestones are these guys, and there are pretty much at all. What's varying down here? What's varying over here? The major variation here, these are all competent rocks. Major variation is porosity. That's what's changing here. Pressure isn't changing. Composition isn't changing, either fluid or, these are the water saturation, either fluid or mineral. So what's changing is porosity along this curve. So you see that the Poisson's ratio of the rock is staying quite constant. And the dolomite has a little lower VP to VS ratio, so lower Poisson's ratio to the limestone. He has a few shale points, I think. Limey sands over here. But the one to look at are these clean sands. And you will notice that as you increase the porosity, you go to greater transit times, lower velocities, that's what that means. You are going to higher VP to VS ratios. Okay, so your sandstones, the VP to VS ratios of the water saturated rock increase. When I said it was 0.15 to 0.2 for sigma cement, the reason I quote you reasonable numbers, a range like that, in fact they vary a little more than that, but there's a reason for that range, and that's reflected in these data. But you can use these for getting VSs from VPs to different rocks. Here's one last one we published. I think I have another take on this now. They were published a couple of years ago, but rock saturated sandstone velocities. These all have similar porosities. They're all measured at the same differential pressure, and they are all clean sands with, not clean sands, they're all sands with some clay or very amounts of clay. What's clay? Clay, to the geologist, is a size. It's not a mineralogic meaning. It has no mineralogic meaning. If I'm going to tell you clay, if I say clay minerals, then I'm talking like a mineralogist. But to a geologist, clay means a size of a particle. It's finer than siltstone. Sand is coarser than siltstone size. So as you put fines in the rock, these are dispersed fines, the velocity decreases substantially. And here's the clay percent by volume of the rock. And it's similar porosity. All of them have porosities within 1% of 5%.
And probably right now, we'd look at this as there's a different architecture, there's a
Right,
different sorting,
yes, exactly.
and the rocks on the right-hand side with more fines tend to be a less competent rock than the ones that tend to be more
Basically, what
monocide.
happens is, what we think is you would have fines in the interstices in the pores that aren't load supporting, and therefore you have a beta in this rock that is more characteristic of a rock with higher porosity than this 5%. That's why the velocity is bigger. Okay. The elastic properties will come down home stretch. Now remember, we've got 2 slides. Elastic properties of rocks of a given type in a given basin vary systematically with depth in young basins due to compaction. That's the stress history. The relationship of VP for sealing rocks to VP of reservoir rocks, which are in contact, is the principal determinant of the amplitude response of a hydrocarbon reservoir. I say that because frequently, though we saw it in that case of Brunei, you will not see strong reflection or a visible reflection down dip on brine saturated sand. Besides VP and porosity, other rock properties are required for calculation of fluid substitution effects. We talked about that. Salinities, GORs, if you have them, pressure and temperature. The properties of all rocks in a section should be characterized. Scatters inherent in the properties of a particular rock type, and you must deal with it. You can't ignore it. You want to reduce it. VS versus VP relationships for some rock types exist from which VS, which is essential for the estimation of the AVO response, may be predicted since VS logs are rare. And I'm going to say a couple of words about VS logs here. Consider a vertical well. You have 2, remember I said this morning that the shear is polarized and perpendicular particle motion of the wave, particle motions are perpendicular to the propagation vector of that wave. So there's 2 polarizations. Polarized vertically and polarized horizontally. So it turns out that when you're going vertical, there's a birefringence. That means a different propagation velocity for rocks, for shear waves that are polarized in one of the 2 principal directions. What determine the principal directions is anisotropy in the basin. That can be a stress anisotropy typically. And birefringences, those seemingly small, only a few percent is sometimes it's quite significant as B2B2BS relations. So just because, Mike made this point earlier, just because you have a shear log doesn't mean that you have a good B2BS ratio. You may be off by several percent. That's why it's often best not to use the shear log when you're predicting the P-wave velocity change. Gardner-Gregg relation, or local empirical density versus velocity relations, like that mudrock relation, which you have derived from one log data, can be used to predict density from velocity when density logs are not available. But don't go the other way around. And low porosity rocks, which may be still good reservoirs, will not have a significant seismic amplitude response to hydrocarbon phase substitution. I dragged that one in from earlier in the day, but that's a reminder. Doesn't mean that quantitative amplitude interpretation is not valuable. It means you can't find hydrocarbons via these. Okay.